Hello everyone. Hi. In this video for the module FC309 integration, and this video is about finding the area enclosed by three functions, or like curve and two lines, or sometimes it's two curves on the line. It's any three functions anyway. All right. So first of all, we know that the area under the curve in general is the integral of y dx. Yeah. So this is the function here, which is f of x or y. So if this is f of x or y, this function here, then we know the area under this curve is the integral of y dx, or f of x dx, or y dx. Why we say this? Why it is y dx? So you remember from last time, yeah, or from the slide, if you look at the slides as well in the PLE, you can see, like, if we have a curve and we can think about the area, under the curve as a small rectangle, as a very, very thin rectangles. Okay, so if we think about it as many thin, very thin rectangles, and we can say that the area it's being made up of many very, very thin rectangles, and the height of each of these rectangles, it's represent y, or f of x. Okay, so we can say this here, it's y, the height for each rectangle. And the width is dx. And basically the width is very thin, that nearly approach to the zero. So it's very, very, very thin rectangles, imagine. So we have these two pictures here, just explaining, like just showing you how they divided or splits the area under the curve into rectangles, and then they split it more to make it much thinner, and that will give more accurate value for the area under the curve. Okay, so if we say let's draw this here as a rectangle here, and therefore this will be the rectangle here. So this is dx, which is the width of it, and this is f of x or y, which is the height. Okay, and so this is the strips here in the middle. If we take another strip, which is, let's say it's here, oh, excuse my drawing, and there's another strip here. Okay, and they meant all to be the same width, so this is y here is different than the other y, and y here is different because basically it's the height. Okay, so this is for now, for this one, just to show you why it is y dx, because if we add up all these rectangles together, imagine there are all this is filled with rectangles, then if we add them up, we will end up with the area of the area under the curve. Okay, So this is just the idea, just to show you how and why. Right, now I will just come to the example which I wanted to show you. Right, so in this example, again, before I start with it, okay, so now in this example here, in this question, let's say we have three functions. We have F1 here, which is the curve. I'm just going to call it F1, just to make it easy when we talk. This is F2, and this is F3. And as you can see, like F1 is a curve, so F1 is a curve, and F2 here and F3, both of them are lines. Okay, so to find the area which is enclosed or bounded between F1, F2, and F3, which is the curve and these two lines, to find the area between them, what we can do is from the previous graph here, when we said the height of each rectangle, it represents the y, or the f of x, and the width is dx. Therefore, the area for each strip, because it's a rectangle, so the area for each strip, it will be the length times the width, which is the height times the width. So the area of each rectangle, it will be y dx. That will give area for each rectangle. Area for each rectangle. Okay, and because under the curve, as we have this big area, and as we said, we can split it into many rectangles, which is very thin. The thickness of it is nearly approaches to zero. Then when we do the integration, it's like we are adding up all these, the area of all these rectangles. So and we get the area under the curve. Right, so what we can do here, it's the same idea. So if we draw a very thin rectangles between the curve F1 and F2 here. Yeah, so this is one of the strips, and the height of it basically is y, and the width is dx. And if we take another strip, basically this is, I'm just explaining to you here what's the idea of it. So they're meant to be all the same width, and the width is approaching zero, which is very thin, that means, and it's too many of them. So I'm just trying to show you what's going on here. So this is the strip, and the height for this strip, as you can see, is different than the first one, because it's the area here, the distance between F1 and F2, it's bigger. And the one here in the middle, is even as well, it's different. So as you can see, if I draw a line here, okay, so this strip, again, all of them, their width are dx, which is the same width, not like what looks in my drawing, because it's not very accurate, my drawing, of course. Yeah, but the idea from it, this is dx here, and the height is y. But I was talking about the area between F1, which is the curve, and which is the curve, this part of the curve, and this line, the red line here, the F2, until I reach this point here in the middle, yeah, which I'm going to highlight in yellow, until I reach this point here, then the area here, it will be changed because this, the other side is going to be between F1 and F3. So it's between the curve and the line F3, the other function. So this strip here is going to be between the curve and F3. So when you find this strip here, the limit for it is going to be maybe same or well, it's this point here and this point here in the middle. Both of them have the same coordinates anyway. But anyway, that what I want to say is when you integrate, you need to use different function after that point because you're dealing with two different functions basically. So this is the y, this is the x, the width of it. And same here, we have this strip here, which is a small. Okay. Right. So as I said, the way we deal with it, it's like we are adding up the area for the rectangles which is enclosed between these three functions. Okay. So we do in that case how to find y. It's basically f1 minus f2 in the left side, which is the red one, which is the red line and the curve. To find y, it's f1 minus f2. And to find y on the other side, it's f1, which is the curve, minus f3. Yeah, to find the height of each strip, basically. Okay, so now I will just give you an example to do the same thing, something similar to solve it. Okay, so this is just, I just wrote this note for you, just to remind you as well. So to find, so basically, briefly, what we do here, this kind of example, we have, as I said, function 1, it's the curve, and the red line is f2, I just call it f2, and the green line is the f3. So it's two lines and one curve. So to find the area which is enclosed between these three functions, such as this example, we do the same thing by breaking down the area into small rectangles, okay? And the width of each rectangle is still dx. I highlighted the things for you to read them and understand. The width for each rectangle is still dx, and the height for each rectangle is going to be the difference between the two functions involved. So what we mean by this, it means for this part on the left, which is the curve and the red line, these are the two functions involved. So it will be y1 or f1 minus f2. Yeah, these are the two functions. And from the other half, which is f3 and f1, it's going to be f1 minus f3, the height of each rectangle, which is the y. And remember that you have to stop your integration after the point of intersection, like I put it here in this example as P, where these two lines, they intersect together at this point. Okay, so you do up to this point. When you reach this point, then your integration needs to change from f1 and f2 into f1 and f3. Okay, at that point. So to stop the integration after the point of intersection P, as the functions are different after this point, so you have to involve the new line, which is F1 and F3. Okay, so basically, in that case, what we will write, the way we will write the integration to find the area, it will be the integral of F1 minus F2 multiplied by dx, yeah, which is the area of F1 minus F2 multiplied by dx, minus plus the other area, which is F1 minus F3, and multiplied by the width is dx. When we do this integration, it's like adding up all the small strips or the rectangles. Okay, so basically that's the whole idea about it. If you think about it this way, that will make things clearer for you and easy to solve. Right, now I will show you an example. I just want you to know the idea, because the numbers of it is a bit complicated. So I just want you to know the idea about it. So if we have the curve, again, same thing, very similar, well, same shape as what I did above here. So I'm just going to draw this now. Okay, so now in this example here, we have the function 1, which is the curve, and then F2 is the line here. I put the same colors, same as the example I explained earlier, and F3 is the other line. Okay, and we need to find the area between the curve and these two lines. As I said, this is the point where they meet together. I'm going to call it here as B instead of P. So let's say this is B, and this point here is A, and this point here is C. Okay, and we want to find the area, the shaded area, which means all this red area, shaded area, and all this other half of it, which is the brown area. I'm going to shade it now. Okay. So this is the other part of it, which is the brown area is include the curve and F3. And the red area is the curve and F2. Okay. Go. Well, it's not very neat, but this is just to explain the idea. I'm not very good at drawing. Okay, now, so the question here is like saying, I'll write it down here for you as well. It's find the point of intersection, find the points of intersection of the three functions shown, and find the area of the shaded region of the shaded region. Okay, so we need to find the area of the shaded area, basically, which is the red and the brown part. Okay, I'll just write down the equations for them. It's a bit not very easy ones. But as I said, this is just as an example to understand how to solve just about the idea. So I'll write it down here. So F1, which is the curve, F1 I'll write it down here. So F1 is the curve. I'll call it's 20. Sorry, x. It's x minus 20 all squared. X minus 20 all squared divided by 30. Actually, it's minus here. Minus x minus 20 squared over 30 plus 20. And F2, which is the red line here, I'll write it down in red. So F2 is 20 over 3 minus x. And the third function, which is the other line, F3, is x over 2 minus 12. Okay, so first of all, as we can see here, to find, well, the question asks to find the point of intersections of the functions. So the point of intersection means the points where do they meet together. So we can see like the red line, which is F2 and F1, the curve, they meet at their intersection point is on the y-axis. So that means the x here equals 0. Yeah, at the y-axis, x equals 0. So for the point A, so to find A here, because they meet at the y-axis, therefore x equals 0. So we can say, and also if you remember, we did this before. To find the intersection point, we make the two functions equals each other. So basically, in this one, we can do F1 equals F2, but because we know in this specific one they intersect at the y-axis, so that means x equals 0. So we can say y equals 20 over 3. So that's the F2 for the line. 20 over 3 minus the x 0 here. So minus 0. And that will give us y equals 20 over 3. Okay, so the point, therefore, the coordinates for the intersection here is 0, that's the x, and 20 over 3, that's the y. So this is the y, and this is the x for the point of A. Okay, so A here is 0 and 20 over 3. Okay, now to find B, we will do the equation for the green line. Sorry, B is the green line and the red line. So it's F2 and F3. So make them equal each other. So the equation for F2 is 20 over 3. So to find B, so to find the coordinates for the point B, we make, let F2 equals F3. So basically, we do 20 over 3 minus x equals F3 is x over 2 minus 12. So we make them equal together. And after you rearrange and tidy up the equation together, the functions, like we can multiply here by both sides by 6. Yeah, to get rid from the fractions here, because we have 3 and 2 at the denominator at the bottom. So if we multiply by 6, we can get rid of it. So after you work it out, we will get 40 here minus 6x equals 3x minus 72, and therefore we will get 112 equals 9x, and x equals 112 over 9. So if x equals 112 over 9, then y is x over 2 minus 12. So we'll substitute by the value of x, which is 112 divided by 9, divided by 2. So that will give us y as minus. So instead of x, we'll write 112 divided by 9, divided by 2 minus 12, and that will give you the value of y, which is minus 52 over 9. Okay, so the point B is, the coordinate for B is 112 over 9, so that's the x, and minus 52 over 9, that's the y. Okay? Right. Now, same thing to find the C coordinates. So to find C coordinates, basically, same thing. We will make, so if you look at C, it's the intersection point between the curve F1 and the line F3. So we make F1 equals F3. So to find C, it's F1 equals F3. So we'll substitute the equations for both of them, the functions for both of them. So that means x over 2 minus 12, x over 2 minus 12, that's F3 here. And F1, which is the curve, so there's going to be minus x minus 20 squared over 30 plus 20 equals F3, which is x over 2 minus 12. And again, we have 2 and 30 at the denominator, so if we multiply by 60, and that's when you work it out, you can figure out these things. So after you multiply, you will get a bit complicated numbers. As I said, this is just to show you the idea of how to solve, not about the numbers and how scary they look here. So this will give you like 30x minus 720 equals minus 2x minus 20 squared plus 1,200. And this again, it's like 30x minus 720 equals minus 2. Now we expand this because it has squared. So this is going to be minus 2 times this. When you expand this squared, it's going to be x squared minus 2 times 20x. So it's minus 40x plus 400. Okay, and plus 1,200 here. So after you tidy up, you move things to the other side, and you multiply out this minus 2 here by this bracket, then you will get as 2x squared minus 80x plus 30x plus 800 minus 720 minus 1200 equals 0. And you can solve this using the quadratic formula. So 2x squared minus 50x minus 112 equals 0. So x equals minus 50 here, minus plus square root of of 50 squared plus 4 times 2 times 1120 over 4. When you work this out from your calculator, you will get the answer as 39.3 or something else. Okay. Anyway, as I said, we are not after the results from these numbers to be complicated, and just after the idea from it. So if x is 39.3, then we substitute this in y. Yeah, so therefore y equals x over to any of the equations, because both of them they meet at this point, so that means at this point it's satisfying. So you can use any of the equations. So y equals x over 2 minus 12. This is for the line, and you substitute the value of x here. So therefore y equals 39.3 over 2, and this will give 7.65. So therefore the coordinates of C is 39.3 and 7.65. So far, we just found the coordinates for A, B, and C, the intersection points. Okay. Now they said find this area, find the area between them. And as I just explained at the beginning, the area in this case is going to be the red area plus the brown area here. Okay? The red area plus the brown area. And the red area, it's going to be, as we said, it means the difference of the height of each, it's the difference for the height of the rectangles between these two curves multiplied by the x, the width of each one. Okay, so this is the x, it's the width of each rectangle. So for the first one, we can say here as the integration of f1 minus f2. Okay, and we need the limits, the x. What's the limit here? We have x equals 0. We're at a, x equals 0 here. Yeah, so from 0 until the point where they intersect, which is B here. What's the coordinates for it? The x for B was 112 over 9. It's a strange number, but okay, so it's 112. This is 112 over 9. That's the x, and the y was at what must be minus 52 over 9. Okay, so the limit is going to be from 0 to x, where the red finish is 112 over 9. Okay, And then the other area, the brown area, will start from x is 112 over 9 up to the value of the x at c, which is 39.3. Yeah, so x here is 39.3. That's for the x. And the y was 7.65. Okay, so finding the area then, this is part 2 now. So area between the three functions is, so if I say area equals the red area plus the brown area, so if I call it Rn plus B, R and B, up to red plus B area, basically. Yeah, it's the red area plus the brown area. Yeah, I'll call this B. This is B, and this is red. Well, you know that. This is just to explain for you, anyway. Now, what's the red area here? The red area is going to be what? As we said, the red area, I will write it in red. Red area, it's basically the integration from 0 to 112 over 9 for function 1 minus function 2 dx. Okay, and then plus the brown area is the integration from 112 over 9 up to what we said, 39.3 for f1 minus f3 here dx. Okay, and in this case, we just substitute the values of them. So this is going to be, I'll just do the red one first here. So separate, you can do them separately and then add them later on. Maybe it's easier rather than just go over them all together. So that's what you need to know, and that's what you should do. And now what I'm going to do, I will work it out. I'm not going to work it out, by the way, just to show you the idea, as I said. So you can just work out separately. So this is from 0 to 100 from 0 to 112 over 9, and f1 is minus x minus 20 squared over 30 plus 20, so that's f1, minus f2 is 20 over 3 plus x, because it's in the questions already it was minus x, so 1 multiplied by this minus in the middle becomes plus, and then dx. Okay, so that's the red one, and then you work it out as after you do the substitution, etc. So plus the other integration, which is the other area, is from 112 over 9 until 39.3, and this is going to be f1, which is the curve, minus x minus 20 squared over 30 plus 20. So far, this is just the curve. Now, minus the line, which is x over 2 the equation for the line was x over 2 minus 12. So minus minus is going to become plus. So it's minus x over 2 plus 12 multiplied by dx. Okay, and you work it out, and you work out the limit, and you'll find the answer at the end for the area. Okay, as I said, these numbers are a bit complicated. Maybe you can get a fractions number as well in your question or something like that. So you just work it out. I don't want to go over this and work it out because it will take a long time. But just want to give you the idea, and I hope this is a bit clear and give you a better idea about it. Okay, thank you very much, and wish you all the best. Bye. Okay, just before we finish, for homework you can do, or to practice, question 2, question 4 from exercise 2.2 from your book, page 118, chapter 9, and also question 10, A, B, C, D, this is in green, and question 14, A, B, C, D, B, C, D, even if you do A, B, C, D is fine. Page 120. Okay, so you can do these for more practice about this topic. Okay, have a nice day and take care, and bye. Thank you very much.